Okay, the next example is going to have us solve another non-right triangle. So we've got some astronauts who use trigonometry to determine the width of craters. They've marked 2 points on opposite sides of a crater. So let's just make a rough shape right here for a crater. And we'll have 2 points on opposite sides of the crater. And a third point, a known distance away from A. And then by measuring the angles BAC and ACB, they were able to use the law of sine to determine the crater. So draw a diagram of what this might look like. Okay, so if I had, this is actually maybe even a right triangle, so maybe C isn't on it. So this is just one particular case. Let me draw another one that's non-right triangle as well. So A, C, B. Just to make the point that this triangle did not have to be right, I just kind of accidentally drew one. That C point could be on the crater depending on how they measured it. And so another diagram, this one might even be a little more accurate towards what the picture was looking for. We've got our diagram. And so the angles that they were talking about measuring, the angle that goes from BAC, that's this one, A is in the middle, so this is our angle BAC. And then the angle ACB, which is this one. So they can measure these two angles in reference to B without having to walk all the way around the crater to get to B and measure the angle CBA or ABC. Okay, so that's my diagram. And then in part C, we have some measures. So just kind of resketching this triangle. I didn't draw my crater again this time, but now I know some things about these points A, C, B. So what we know now is that C is 50 meters from A, so this side is 50. The angle BAC is 112. So my picture's not to scale, that's okay. ACB is 42, definitely not to scale in this picture, that's all right. So what is the width of the crater? Okay, so the width of the crater, what we're trying to find, based on the original diagram, we're looking for the distance between A and B. So this is what we're looking for. So this is still our goal. And so that's our little c that is our goal. Okay, so law of sines would get it for us if I knew, I need to know the match to this side. So this is little b, I need to know angle B. So I can use 180 degrees for a triangle to find that. So 180 degrees minus the 112 minus the 42 gives us 26 for our B. That's the first thing we need to know, is that angle. So B is 180 degrees minus 112 degrees minus 42 degrees. So it's 26 degrees. So now we know this little angle is 26 degrees. And so now I have a pair that match here, opposite side to that angle, and I can use that with law of sines to get opposite side to angle C. So we can set this up as little c over the sine of 42 degrees equals 50 over the sine of 26 degrees, and multiply the sine of 42 over, and we'll get our side solved for. So little c equals sine of 42 degrees times 50 divided by sine of 26 degrees. So I'll make sure my calculator is still in degrees. Yep, and so I can calculate this. So sine of 42 times 50 divided by sine of 26. And so little c is 76.32. Did I have a distance for this? Meters. Okay, meters. So it seems like here that the crater is 76.32 meters wide. Okay, now we're going to check out some other angles or triangles that we can solve here. So this time now we have two sides and an angle. Okay, so if I know two sides at an angle, I can't use subtraction to find the other angle, but I can use the law of sines to find the missing angle. I do need to be careful with this though. Let's read the note here above. Okay, it's possible to have situations like this where I know two sides at an angle, where there are no solutions, one solution, or even two possible solutions. So you've got to be careful with these, and we'll explore the options for these. So we'll talk about that. Okay, so let's see what's going to happen in this first one. Is there one answer? Are there two answers? Is there no solution to this triangle? Let's find out. All right, so here, let's say since we know the pairing of CC, we're going to use that. I can't go for A first because I don't know either part of A, so I'm going to have to go for B first. Okay, so we're going to set up the CC pairing. Because I'm looking for an angle, I'm going to put the angles on top. So we're going to do the sine of the 45.6 degrees over the 34.2, sine C over little c, and then sine B over little b, 42.1. And now if I multiply this side over, I'll have the sine of b by itself. Okay, and so let's finish that multiplication. We have to take 42.1 times the sine of 45.6 divided by 34.2, and that gives us a sine B value of 0.8795 for sine of B. Okay, now we are going to take the arc sine of this value, but what we're going to keep in mind is that the sine ratio is positive, so that means that there are two possible angles right now that could have a sine value of 0.8. They are both up here somewhere. So we need to find both since this is a positive ratio. I'm looking in quadrants 1 and 2 up there. And so to find our angle, we're going to have the arc sine of 0.8795 is going to be equal to our angle B. So arc sine of this number, oops, too far, gives us an angle, or a B value, of 61.58 degrees. Now I need to find the other one, the one that's 60 degrees away from the negative x-axis. And so if I take 180 minus the 61 degrees, that gives us the other angle as 118.416 degrees. Now we can check those, because if I take the sine of that new angle, I should have the same trigonometric ratio that I had before. So yes, those two angles have the same sine. So currently I have two possible solutions here that I could have, because 118 is not too big to be an angle in a triangle. So I may have a 118 degree, or I may have a 61 degree. And so we're going to find out which of those is correct as I complete the triangle. Maybe both will work this time. Let's find out. So we've got two scenarios now, and so we're going to divide our page over here and work through both of them. Okay, so in the first case, we're looking at the B value being 61.58 degrees, and in the second case, we're looking at the B value being 118.416 degrees. Okay, I guess if I wanted to keep the same number of places, I could have rounded this one to 42. We'll do that. So 42 degrees, just to keep just two places on both, since everything else is in one place. Okay, now for each of these, let's find the angle A. And so in the first one, angle A would be 180 minus 45.6 minus 61.58. So that gives us 180 minus 43.6. Oops, 45.6. I can't read my own writing there. 45.6 minus 61.58. So this would give us an angle A of 72.82 degrees. Versus if I had a different measure for B, if I take the 180 degrees minus the 45.6 minus the 118.42, this gives us an angle A measure of 15.98 degrees. Okay, so if one of those had come out negative because angle B was just too large to fit inside the triangle, I would know that that one wasn't going to work. So right now, so far, it looks like both are possibilities. I have an angle that sits inside the triangle. All right, so I know let's see, I know angle B for two possible angle B's, and I know angle A for two possible angle A's. The only thing I'm missing right now is side A, so let's go ahead and find side A for each of those. Okay, so we're going to use the known ratio that we had along with the new angle for A. So in the first one, we would set up something, we're looking for a side, so we're going to put the sides on top. So we'll have 34.2 over sine of 45.6 equals little a over sine 72.82, because that's our angle A in this case. In the other case, it's going to be 34.2 over sine 45.6 equals a over the sine of 15.98. Okay, and so if I multiply the sine over to solve for a in both cases, I'm going to have the sine of 72.82 times the 34.2 divided by sine 45.6. And so this one would give me an A value of 45.73 as a side length. If I did the other one, it's a sine of 15.98 that gets multiplied over times the same thing, the 34.2 over the sine of 45.6. And so this one would give me an A value of 13.18. Okay, so there are two ways to solve this triangle. Depending on whether or not the picture is actually drawn to scale, we can tell if it was the 61 or the 118. This angle looks bigger than 90, so based on the diagram, we might say, hey, this one was supposed to be the 118 if my diagram was actually accurate. I don't know that it was, because if I'm given something like this where I just know distances and I don't have an accurate diagram, it really could be both possibilities. So we have two solutions to a triangle that has these three given measures. There are two different solutions. So one of the solutions is going to have an angle B of 61, an angle A of 72, and a side A of 45. The other solution would have an angle B of 118, an angle A of 15, and a side A of 13. Based on the way this picture looks, it is most likely that the second set is the correct set, that the angle A is only 15 degrees and side A being the shortest is 13. That would fit the diagram. So if the diagram is drawn to scale, we could eliminate this possibility and go with just this one. But right now, again, a lot of times when I draw a diagram, I'm not drawing it to scale necessarily, so we can't guarantee that this one has to be ruled out from what we know right now.